Hello, let's talk about priority queue or heap, commonly used data structure in the algorithmic questions. So it's a binary tree that maintains each node value being smaller than its children for the min heap or like larger for like max heap. The top element of the heap is the smallest or corresponding largest among all of its elements. Popping the top element and adding a new element can be done in O log k time, where k is the size of the heap while maintaining this heap property. It can be implemented by an array where a node at index I has children at nodes 2 times I and 2 times I plus 1. And also some like programming languages have built-in priority queue data structure, or there are some like which allow you to like call library functions to work on heap elements from some array and treat array as a heap. So priority queue is useful for problems where some partial sorting is needed or consistently finding the smallest or largest element as the element keeps getting updated. Let's take a look at a classic example of heap sort. So the problem is sorting, given that the elements sort them in ascending order. So first step, we build an array into a maximum heap to have a heap property. We go from the back and push element downwards to the child nodes if the heap property doesn't hold. So since most elements at low heights, overall time complexity actually ends up being ON. So it's like half of elements are leaves. So we don't do anything pretty much, just check if it's leaves. Then a quarter of elements are at height 2, and so on. So then we do another iteration to sort the elements. At every step, we swap the top element with the last element, which is still in the heap, we treat it as an array, and push the new top element downwards to the child nodes until the heap property holds. So each such step takes log n time, resulting in O log n overall time complexity. And in the end, since we pick largest element at each step, largest remaining, then like we're gonna have it sorted. So then next problem is merging k sorted arrays. So given the k sorted arrays, merge the elements into a new array in a sorted order, ascending. So we use k-pointers approach for tracking what's the current element of each of the k arrays we're currently processing, starting with 0, and then choose the smallest element in each step. To pick this smallest element more efficiently, we'd use a heap. Heap element would be a tuple with like value, array number, and index in the array. The value is needed for ordering, while the array number and index would be used to find the next element in that array to process. Or alternatively, skip it if you already reached the end. Note that if some arrays are originally empty, they shouldn't even get added to the heap. We keep iterating while the heap has elements. The overall time complexity ends up being m log k, where m is the total number of elements in all arrays. It's pretty good. So then let's check homework. I encourage you to like pause the video after checking this out, then try to solve it yourself. And then I would be giving some solutions as well. So first problem, given an array of n elements and number k, compute the minimum element in each subarray of length k. For example, if a is equals to 1, 3, 2, 7, 4, k is equals to 3, then answer would be like 1, 2, and 2. Another problem, given an array of n elements, compute the running median of each subarray starting from the first element, or like zeroth element. Example, if like a is 1, 3, 2, 7, 4, then we get like 1, 1, 2, 2, and 3. Note that I'm picking like smaller of like 2 median elements when selecting the median for like the even lengths. Sometimes you just need to select like average, so you need to kind of clarify and see like what it is in the case of like even elements. Another problem is like given a graph of n vertices and m edges with weights wij, compute the weight of the minimum spanning tree. So graph subtree where all vertices are connected by some path from the edges we've picked. The total weight of those edges is the smallest possible, and graph is connected. Okay, so pause the video, try to solve those, and then come back for an analysis of these problems. Okay, so let's try to check the first problem. So the first problem is gonna be used by this priority queue of size k. We first populate it, then we need to like have a sliding window where we add a new element and remove old element. Since old element is like not necessarily at the top of the heap, we need some like additional index and reverse index to see like where the element is in the array and in the heap. And this way we can just like swap it with the last element and like restore the heap property in logarithmic time. And then we just like look at what's at the top of the heap. And this is gonna be n times log k complexity. So for second problem of median, it's a bit trickier. We're actually gonna have like two heaps, maximum heap and minimum heap. And the idea is we're gonna maintain that like elements are split in half, where like that we try to maintain that like two heaps are in the way that like if they're unequal size, then we pick from the larger heaps the element and it's gonna be our median. Otherwise we pick like if the heaps are equal, then we pick either like average or pick the smaller elements. So now that we first just pick the first two elements and add smaller one to the max heap and larger one to the small heap. Then at next step we check, hey, is the next element, in this case 2, is it smaller than the large heap top? In this case large heap has 1, so it's not, so we add 2 to mean heap, so like mean heap becomes 2 and 3. So and then like mean heap is bigger, so we return top of it, which is like 2 as the next element. Then we pick 7. In this case 7, is it like smaller than the root of max heap? No, it's like bigger. So we add it to the mean heap. Mean heap again becomes 2 in the top and 3 and 7 as the leaves. So this way we need to like rebalance now because we get like sizes difference by more than 1. So we remove 2 and add it to the max heap. So we get max heap is like 2, 1. Mean heap is 3 and 7. So then we pick like 2, or in some cases we can pick like average between 2 and 3, depending on what the problem requires, and put it as a median. So then we get 4. Again, is it like bigger than or is it smaller than the root of max heap? No, it's not. So we add it to the mean heap. So mean heap becomes like 3, 4, and 7, and it's larger now. So we pick root of mean heap, which is like 3, and put it as a result. So we try to maintain that those like max heap contains smaller part of elements and mean heap contains larger part of elements. And we do like rebalancing if needed. So yeah, that's like that's not non-trivial concept to get to. So don't feel bad if you didn't solve it yourself. And the last problem is with a graph. Actually, what we're gonna do is we're gonna take the edges and add them to the heap, and alternatively we can sort them as well. So then we go from the smallest edge and we check, okay, when we now have like, first we have like n disconnected vertices. So we assign some index, sort of a color for each of them. And then when we like pick a next edge, we check, hey, does it connect the elements of the same color? If it connects elements of the same color, we do nothing. If it connects elements of a different color, we like connect those groups now, and we need to recolor. So we pick like a smaller color group and recolor it into a larger color. So like it's gonna be like a symptotically better time. So, and that's pretty much it. There are some other data structures which can make this like basically regrouping faster. But don't worry about this for now. So we're still gonna get like m log m or like m log n time complexity. And yeah, the property is at each step we just need like the smallest edge out of the edges remaining. So yeah, that's gonna be it for me for today. Thanks for watching. Let me know if you have any questions.